These are the machines that would vanish forever, permanently, irretrievably, if the people running them ever lost the ability to talk to them across billions of miles of empty space. This is the actual, verified story of how NASA and other space agencies keep in contact with spacecraft so far from home that a single message can take nearly 2 full days just to make the round trip, and how a handful of engineers, working with nothing but radio waves and careful math, have managed to land probes on moons, comets, and planets they could never see with their own eyes in real time. If you're new here, stick around, because by the end of this you'll understand something very few people ever stop to think about. How do you steer something you can't see, can't touch, and in some cases can't even talk to fast enough to save if something goes wrong? Hit like, subscribe if you want more of this, and let's get into it. Most people assume that once you're out in space, navigation works the same way it does everywhere else. You've got GPS on your phone, you've got GPS in your car, so surely a spacecraft heading to Pluto just uses some deep space version of the same thing. It doesn't, and it can't. GPS is a system of satellites orbiting Earth, built specifically for use in and around our own planet, and the moment you leave that neighborhood, the whole system stops working. NASA and its Deep Space Network define deep space with a very specific starting line. Anything past the Moon's orbit counts, and that boundary marks the exact point where the rules of navigation change completely, permanently, for the rest of a mission's life. So if a spacecraft can't check its GPS, how does it know where it is? The answer is almost stubbornly old-fashioned when you get down to it. A spacecraft in deep space navigates using precisely timed radio signals, sent back and forth between the ship and Earth, over and over, for years, sometimes for decades at a time. Navigators on the ground track the spacecraft's location and its speed from those signals, and then they transmit course corrections back up to it. That's the whole system, at its core. No beacons floating around the solar system, no satellite constellation out past Mars, just radio waves, precise clocks, and a team of people doing math that would make your head spin. And as you're about to hear, sometimes doing that math wrong has cost entire missions everything. The infrastructure that makes this possible is called the Deep Space Network, or the DSN, and it's run by NASA's Jet Propulsion Laboratory. It isn't one antenna, and it isn't even one location. It's 3 separate complexes, spaced out across the globe. One at Goldstone, in the California desert near Barstow, one near Madrid in Spain, and one near Canberra in Australia. And the spacing isn't random. Those 3 sites sit almost exactly 120 degrees apart from each other around the planet, which means that as Earth spins on its axis, at least one of those dishes always has a clear line of sight to any spacecraft, anywhere in the solar system, at any hour of the day or night. When one station rotates out of view, another has already rotated into position, a relay system built into the shape of the Earth itself. These aren't small dishes either. The DSN communicates using several radio bands, including S-band, X-band, and the higher frequency Ka band, and the antennas involved rank among the largest steerable structures ever built by human hands. And the network does more than send commands and receive data. Scientists also use the tiny, measurable changes in those radio signals to study the rings of Saturn, to probe the interior structure of planets and moons, and even to test predictions from Einstein's theory of relativity. A system built to, say, turn left to a robot near Neptune also happens to be one of the more sensitive scientific instruments humanity has ever constructed. Now here's where it gets genuinely clever, because knowing that you can talk to a spacecraft is one thing, and actually figuring out exactly where it is, and where it's going, is a completely different problem. And the way engineers solve it comes down to a method that sounds almost too simple to work. They use time itself as a measuring tape. It's called ranging, and here's how it works. The Deep Space Network sends a signal out to a spacecraft. The spacecraft, upon receiving it, immediately sends that same signal straight back. Mission Control on Earth then measures exactly how long that whole round trip took, down to fractions of a second. And because radio waves travel at the speed of light, a fixed and known number, that travel time converts directly into distance. Divide the round-trip time in half, since the signal made the journey twice, and there's your answer. The accuracy involved is staggering. Using this method across distances measured in billions of kilometers, modern ranging can pin down a spacecraft's distance to within a matter of meters. Distance alone isn't enough, though. Navigators also need to know how fast the spacecraft is moving and in which direction, and for that, they rely on something called the Doppler effect, the same physical principle that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it drives away. As a spacecraft moves relative to Earth, the frequency of its returning radio signal shifts slightly, and by measuring that shift with extreme precision, engineers calculate the spacecraft's velocity. Keep that idea in your back pocket, because later in this story, that same Doppler shift very nearly ruined one of the most ambitious landings ever attempted in the outer solar system. Then there's a third technique, arguably the most elegant of the three, called Very Long Baseline Interferometry, or VLB. Instead of using just one antenna, engineers use multiple DSN antennas simultaneously, spread out across the globe, to essentially triangulate a spacecraft's exact position, achieving accuracy down to a fraction of a kilometer. Combine ranging, Doppler shift, and VLB together, and you get a navigation system precise enough that engineers can predict, years ahead of time, exactly where a robotic spacecraft will be at a specific second on a specific day, even after it has traveled for a decade through empty space. Radio isn't the only tool in the box, though. Some missions also carry cameras built specifically for navigation, a technique called optical navigation. Rather than relying purely on signals bounced off Earth, the spacecraft photographs its actual destination, whether that's a planet or a moon, against the fixed backdrop of distant stars, and those images let navigators refine the spacecraft's position independent of any radio measurement at all. When NASA's New Horizons mission approached Pluto, it used exactly this kind of imaging, captured by an onboard camera called LORRI, to sharpen its aim during the final stretch of a 9-year journey, a story we'll come back to. And building all of this into a coherent flight path required more than clever engineering. It required accounting for the actual physics of the solar system itself. Navigators correct for delays caused by Earth's own atmosphere, for interference from solar plasma streaming outward from the Sun, and even for the subtle effects predicted by relativity, which become measurable at these distances and speeds. On top of that, mission planners use the gravitational pull of planets themselves, timing a spacecraft's path so it swings close enough to a planet to steal a little of that planet's momentum and get flung onward toward its next destination, without burning through fuel it doesn't have to spare. This single idea, the gravity assist, shows up again and again throughout this story. It's how Galileo reached Jupiter, how Cassini reached and then maneuvered around Saturn for 13 years, and how a spacecraft called Parker Solar Probe, which we'll get to later, used the planet Venus itself 7 separate times, essentially as a set of brakes to fall closer and closer to the Sun. None of this precision existed by accident, and none of it happened quickly. To understand how strange and difficult this problem once seemed, you have to go back to the very beginning, before NASA even existed. The roots of the Deep Space Network stretch back to January of 1958. At that point, NASA hadn't been created yet. The Jet Propulsion Laboratory, working under a contract with the US Army, deployed portable radio tracking stations in 3 places: Nigeria, Singapore, and California. That same month, the Army successfully launched Explorer 1, the first successful American satellite, and those scattered ground stations received its telemetry and let engineers plot its orbit. NASA itself wasn't formally established until October 1st of that year, created specifically to pull the separate, competing space programs run by the Army, the Navy, and the Air Force into one civilian agency. Just 2 months later, on December 3, 1958, JPL was formally transferred from the Army to NASA and handed the job of designing and running robotic missions to the Moon and the planets. That same year, the first large antenna that would eventually become part of the DSN, an 85-foot dish, went up in the Mojave Desert at what's now called the Goldstone Tracking Station. Over the following years, this scattered collection of stations slowly grew into something more organized. In February of 1961, a 26-meter antenna near Woomera, Australia, was formally switched on, and in a nice bit of theatre, engineers celebrated the occasion by bouncing a congratulatory radio message all the way from Washington, D.C., off the surface of the Moon, and down to the new dish in the Australian outback. But these facilities, known then as the Deep Space Instrumentation Facility, still operated mostly on their own, independently of each other, for years. That finally changed on December 24, 1963. On Christmas Eve, JPL's director at the time, William Pickering, signed a memo formally merging the tracking stations, the communications systems between them, and the mission control operations at JPL into one unified structure. He gave that structure a new name, the Deep Space Network. 60 years later, in December of 2023, NASA marked that same date as the DSN's 60th anniversary, a network that had, by then, guided spacecraft to every planet in the solar system and beyond. The man most closely associated with building that network is an engineer named Eberhard Rechtin, often called the father of the Deep Space Network. Rechtin directed the project and served as an assistant director of JPL from its very inception in 1958 until 1967, when he left to join the Department of Defense, eventually running the Advanced Research Projects Agency, the organization that would later become DARPA. Long before any of that, back in the 1950s, Rechtin had developed something called microlock, a clever system of receivers spread across different ground stations that could compensate for the way a rocket's radio frequency shifts as it accelerates through flight. That early work became the direct foundation for Codirac, the coded Doppler, ranging and command system that Rechtin developed along with engineers Richard Jaffe and Walt Victor, and Codirac became the electronic backbone of the entire early tracking network. A colleague of Rechtin's, engineer Susan Finley, was part of the team that built the network's early software, work that quietly underpins the same basic tracking system still in use today. What's remarkable is just how much skepticism Rechtin faced at the very beginning. In a 1995 interview, recorded as part of an oral history project for the Institute of Electrical and Electronics Engineers, Rechtin looked back on those early days and described being told, flatly, by people who had won Nobel Prizes, that it simply would not be possible to maintain communication all the way to the edge of the solar system. And even if it somehow were possible, the argument went, the resulting signal would be so weak and degraded that you'd need impossibly wide receiving bandwidths just to compensate for the shifting frequencies, and impossibly powerful transmitters, sending out megawatts of energy just to be heard at all. Rechtin and his team built the system anyway. Today, that same basic architecture, refined and rebuilt many times over the decades, is what lets engineers exchange data with a machine that's currently more than 20 billion kilometers from home. Proof that the whole idea actually worked came surprisingly fast. On November 28, 1964, NASA launched Mariner 4, aimed at becoming the first spacecraft in history to successfully fly past another planet. It almost didn't happen at all. Mariner 4's identical twin, Mariner 3, had failed just weeks earlier when its protective shroud refused to separate, leaving its solar panels pinned shut and the spacecraft drifting, dead, into an empty solar orbit. On December 5, 1964, with Mariner 4 already about 2 million kilometers from Earth, engineers fired its small course correction engine for just 20 seconds, nudging its velocity by a mere 17.3 meters per second, a single small adjustment that determined 7.5 months in advance whether the entire mission would succeed or fail. It worked. On July 14th and into the early hours of July 15th, 1965, Mariner 4 swept past Mars at a distance of about 9,846 kilometers, and its onboard television camera captured 21 full images, plus part of a 20-second, covering roughly 1% of the planet's surface, the very first close-up photographs any human being had ever seen of another planet. Data rates back then were almost unimaginably slow by today's standards, only about 8.33 bits per second through the Deep Space Network's 26-meter antennas, so those images, initially stored on an onboard tape recorder, took about 4 days just to fully transmit back to Earth. About an hour and a quarter after closest approach, Mariner 4 slipped behind Mars, as seen from our planet, and its radio signal briefly cut out entirely, an interruption engineers had planned for on purpose, because studying exactly how that signal bent and faded while passing through the thin edge of the Martian atmosphere told scientists just how sparse that atmosphere really was, Information that directly shaped the design of every single Mars lander that came after it, since it proved parachutes alone would never be enough to slow a spacecraft down. Landers would need retro rockets too. And in March of 1966, a brand new 64-meter antenna at the Goldstone Deep Space Network complex in California received its very first signals ever, fittingly, from Mariner 4 itself, earning the dish an informal nickname that stuck even after its official dedication the following month, the Mars Station. Not every navigation story in this history depended on the Deep Space Network at all either. Some of the most remarkable course corrections ever made in spaceflight happened much closer to home, using nothing but a window, a landmark on Earth's surface, and a wristwatch. On April 11, 1970, Apollo 13 launched from Kennedy Space Center, bound for the Moon. Roughly 56 hours into the flight, an oxygen tank in the spacecraft's service module exploded, crippling the ship and turning a lunar landing mission into a fight simply to get 3 astronauts home alive. Apollo missions were normally flown along something called a free return trajectory, a flight path engineered so precisely that the Moon's own gravity alone, with no engine firing required at all, would sling the spacecraft back around and send it heading toward Earth, a built-in safety net baked directly into the shape of the flight path itself. Apollo 13, though, had already been nudged off that safe trajectory onto a slightly different path before the explosion happened, which meant that after the accident, the crew's very first priority was firing the lunar module's small descent engine for about 35 seconds, just to get the crippled spacecraft back onto that free return course, because without it, they'd have sailed thousands of kilometers past Earth entirely. That wasn't the last correction needed though, and the final one might be the single most human moment in this entire story. With the command module's main navigation computer and guidance systems completely powered down to conserve what little electricity remained, and with a cloud of vented debris drifting around the spacecraft, making it nearly impossible to get a clean sighting on the stars the system normally relied on, flight controllers on the ground needed another way to point the ship in exactly the right direction for one final, critical engine burn. A navigation specialist on the ground named Charles Dietrich remembered an old technique, originally developed for earlier missions flown in Earth orbit. Use the visible line on Earth's surface where daylight meets darkness, the terminator, as a fixed point of reference, and align the spacecraft against it by eye. On April 17, 1970, at roughly 105 hours and 18 minutes into the mission, the crew carried out exactly that maneuver. Commander Jim Lovell watched that boundary between day and night through a window, using it to hold the spacecraft's orientation steady while firing the lunar module's engine. Lunar module pilot Fred Hayes fired small thrusters to settle the propellant in the tanks and kept an eye on the spacecraft's pitch. And command module pilot Jack Swigert timed the whole thing, watch in hand, and called out when it was time to shut the engine down. The burn itself lasted about 14 seconds. 3 astronauts, a glowing line across the edge of the Earth, and a matter of seconds, and it worked. Apollo 13 came home safely, and that same manual technique, born out of a genuine emergency, was later folded into the standard training given to every Apollo crew that flew after it. Long before there was a deep space network sophisticated enough to guide something to Pluto, this is what deep space navigation sometimes actually looked like. Not a room full of computers, but 3 men, a window, and their own 2 eyes. More than half a century later, NASA effectively repeated that same stress test, minus the emergency and minus the crew. On November 16, 2022, at 1:47 in the morning Eastern Time, a new spacecraft called Orion launched atop NASA's new Space Launch System rocket on a mission called Artemis 1, the first fully integrated flight of the hardware meant to eventually carry astronauts back to the Moon. Nobody was on board, but the entire point of the mission was to push every one of Orion's deep space systems, including its navigation, as hard as a real crewed flight one day would. On its 7th day in flight, Orion's dedicated optical navigation camera photographed the far side of the Moon from about 81 miles above the surface, gathering exactly the kind of imagery, under exactly the kind of varying light, that future crews would need the system to handle reliably. On November 25th, flight controllers fired Orion's main engine for 1 minute and 28 seconds, nudging its velocity by a few hundred feet per second, and settled the spacecraft into what's called a distant retrograde orbit around the Moon, a deliberately chosen path so stable it barely needs any fuel at all to maintain, even far out in deep space. The very next day, Orion broke a record that had stood since 1970, farthest distance ever traveled by a spacecraft built to carry human beings, a record set by Apollo 13 itself during its own crisis, at 248,655 miles from Earth. Orion eventually pushed that mark out to 268,563 miles before turning for home, using one final precisely timed lunar flyby and a gravity assist from the Moon to slingshot itself back toward Earth, re-entering the atmosphere at roughly 25,000 miles an hour and splashing down safely in the Pacific on December 11, 2022. One mission manager called it, simply, a genuine stress test of the whole spacecraft under real deep space conditions. It was, in a very real sense, Apollo 13's Terminator and wristwatch problem, all these decades later, but rehearsed on purpose by a machine before any human being would ever have to rely on it for real. 6 years after Apollo 13 splashed down, that same deep space network, only about a decade old by then, faced its first real test of landing something on another planet entirely, without any astronaut on board at all to watch the Terminator or fire an engine by hand. Viking 1 launched on August 20, 1975, and spent roughly 11 months crossing about 500 million miles of space before entering orbit around Mars on June 19, 1976. The landing had originally been scheduled for July 4 of that year, timed deliberately to coincide with the 200th anniversary of the United States, but engineers delayed it after orbital photographs revealed the planned landing site was too rocky to risk a touchdown. A new site was chosen instead, in a region called Chryse Planitia, and on July 20, 1976, 7 years to the day after Apollo 11 first put astronauts on the Moon, Viking 1's lander separated from its orbiter and safely touched down on the Martian surface. It was the first spacecraft in history to successfully land on Mars and transmit data and images back to Earth. A Soviet lander had technically reached the surface 5 years earlier, in 1971, but lost contact before it could send back anything useful at all. At the distance Mars sat from Earth that day, a radio signal needed close to 20 minutes just to make the one-way trip, meaning that, exactly like every Mars landing that would follow it for the next 5 decades, Viking's entire descent had to be carried out completely on its own, guided by a pre-programmed onboard computer with no possibility of any real-time human input whatsoever. When the signal confirming a safe landing finally did arrive, it was picked up by the same deep space network described throughout this whole story. Its 85-foot antennas in Spain, Australia, and Goldstone, California, still barely a decade removed from the December 1963 memo that had first given the network its name. Viking's lander was independent enough that its onboard brain, officially called the Guidance, Control and Sequencing Computer, could keep operating entirely on its own for its first 22 days on the Martian surface, using nothing but instructions stored in its memory before it ever left Earth. And in a quiet bit of scientific bonus material, Viking's mission also turned into an accidental proof of one of the most famous ideas in physics. By precisely timing radio signals sent back and forth between Earth and the spacecraft, using exactly the same ranging principles described earlier in this video, scientists noticed that whenever the Sun passed nearly directly between Earth and Mars, those signals took very slightly longer to arrive than expected, delayed by the Sun's own gravity bending the space the signal had to travel through. The size of that delay matched, precisely, what Einstein's general theory of relativity had predicted decades earlier. A network built purely to land a robot safely on Mars ended up, almost as a side effect, confirming one of the deepest ideas about the structure of the universe itself. Viking 1's lander went on to operate for more than 6 years, far outliving its planned 90-day mission, and it held the record for the longest surface mission on Mars for more than 3 decades, until NASA's Opportunity rover finally surpassed it in 2010. Before we get into the missions that pushed this system to its absolute limits, it's worth sitting with one particular failure, because it shows exactly how little room for error this whole approach actually leaves. and how a mistake that has nothing to do with radio signals at all can still destroy a mission just as completely as a lost connection would. In December of 1998, NASA launched a spacecraft called Mars Climate Orbiter, designed to study the Martian atmosphere and climate, and to serve as a communications relay for a companion lander that would follow a few weeks later. For 9.5 months, the spacecraft cruised toward Mars, guided the whole way by the same kind of precise tracking used on every other deep space mission. But somewhere in the handoff between two different engineering teams, something went quietly, catastrophically wrong. One team, at Lockheed Martin in Colorado, had calculated the force produced by the spacecraft's small trajectory correction thrusters using pound-force seconds, the standard unit in American engineering. The navigation software on the other end, run by JPL, was built to expect that same data in Newton seconds, the metric equivalent. Nobody caught the mismatch. The result was a discrepancy of more than 4 times between the force engineers thought the thrusters were producing and the force they were actually producing, and that error compounded, quietly, correction after correction, for months. 24 hours before the spacecraft was due to enter orbit around Mars, engineers calculated it would pass about 110 kilometers above the surface. The absolute minimum safe altitude, the point below which the atmosphere would be too thick and the spacecraft would burn up, was around 80 kilometers. By the time engineers recalculated using the spacecraft's actual, corrected trajectory, the real number was far worse. The orbiter was on course to pass just 57 kilometers above Mars, deep inside the danger zone. Then Dr. Edward Stone, the director of JPL at the time, later acknowledged publicly that the failure to catch such a basic error had serious consequences for the entire mission. Last contact with Mars Climate Orbiter came on September 23, 1999. The spacecraft, a $125 million piece of hardware that had traveled nearly the entire distance to Mars successfully, was almost certainly torn apart or burned up in the thin Martian atmosphere, destroyed not by any flaw in the deep space network, not by any breakdown in radio communication, but by 2 teams of brilliant engineers who never checked, carefully enough, that they were speaking the same mathematical language. If Mars Climate Orbiter shows what happens when a tiny, invisible mistake slips all the way through to the end of a mission, Galileo shows the opposite lesson entirely, because its failure happened early, in full view of everyone, and engineers spent years fighting it rather than accepting it. Galileo, NASA's flagship mission to Jupiter, launched on October 18, 1989. It carried a large, umbrella-like high-gain antenna, designed to unfold in space and become the spacecraft's primary means of sending back the huge volumes of imagery and scientific data the mission was built to gather. On April 11, 1991, controllers sent the command to open it. It didn't work. The antenna's 18 individual ribs were supposed to swing outward together, like the ribs of an umbrella catching the wind, but only some of them made it. NASA immediately assembled what engineers called a Tiger Team, a group of specialists from multiple disciplines, along with outside contractor consultants, to figure out exactly what had gone wrong and whether there was any way to fix it, from a spacecraft that was, by that point, already deep in space and moving farther away with every passing day. The investigation eventually pointed to something almost absurdly small as the likely culprit: friction, in a pin and socket mechanism at the midpoint of a few of those ribs, probably just 3 of them, most likely caused by the loss of a thin lubricating coating sometime during the antenna's handling and storage before launch. For nearly 2 years, engineers tried everything they could think of to physically free those stuck ribs. They warmed the antenna in direct sunlight, hoping heat might loosen whatever was binding it. They tried repeatedly pulsing the small motors responsible for the deployment, hoping vibration alone might shake it loose. An attempt in June of 1991 to warm the mechanism failed outright. Engineers even devised a plan to try the opposite approach entirely, deliberately cooling a central support column, hoping it would contract just enough to release the stuck ribs, an attempt planned for a point later in the mission when Galileo would be even farther from the sun's warmth. None of it worked. After nearly 2 years of trying, the antenna simply would not open. Here's what made that failure so serious. Without the high-gain antenna, Galileo's only option was its small, low-gain backup antenna, a system never designed to carry the mission's actual data load. Contemporary estimates from the time were stark. Using only the low-gain antenna, it would have taken roughly 12 days just to transmit a single image of Jupiter back to Earth, and something like 2 years to send back a total of around 60 images, compared to the thousands of images the mission had originally been designed to capture in that same stretch of time. For a mission that had already cost well over $1 billion, and whose entire scientific value depended on returning enormous amounts of imagery and data from one of the most complex environments in the solar system, this was close to a mission-ending catastrophe. NASA didn't give up. Rather than accept that outcome, engineers spent from 1993 to 1996 years rewriting the mission almost from scratch. They built entirely new flight software to run on the spacecraft itself and entirely new ground-based systems, including significant upgrades to the deep space network, all specifically engineered to compress, prioritize, and squeeze as much of Galileo's planned science as possible through that same small, low-gain antenna that had never been meant to carry it. It worked. Galileo went on to spend years in orbit around Jupiter, studying the giant planet and its moons, ultimately returning the majority of its planned scientific results, not because the original hardware performed as designed, but because a team of engineers on Earth, working at a distance of hundreds of millions of miles, essentially reinvented how the mission communicated, without ever touching the spacecraft itself. And along the way, on October 29, 1991, while all of this was still unfolding, Galileo also became the first spacecraft in history to fly past and photograph an asteroid, a reminder that even a mission fighting for its communication life kept making history in the meantime. Galileo actually launched the same year as another NASA mission, one aimed at a completely different planet, and one that, by contrast, went almost entirely according to plan. NASA's Magellan spacecraft was released from the cargo bay of the Space Shuttle Atlantis in early May of 1989, and an attached booster rocket sent it on a roughly 15-month journey covering more than 1.5 billion kilometers, not because Venus is especially far away, but because of the particular looping trajectory needed to get there efficiently. On August 10, 1990, Magellan fired its engine for 83 seconds and settled into orbit around Venus. Venus presents a navigation and science problem all its own. The entire planet is wrapped in thick, permanent cloud cover, meaning an ordinary camera would show nothing but blank white haze, no matter how close you got. Magellan's solution was radar. Its main instrument beamed radio waves straight down through those clouds and measured what bounced back, building up a detailed picture of the actual rocky surface underneath, a technique that doesn't care whether the sky above it is clear or not. The mission's very first radar test, conducted August 16, 1990, split its data across 2 Deep Space Network stations, one strip landing at Goldstone in California, the other at Canberra in Australia, the same globally spaced trio of dishes that runs through every single story in this video. Formal mapping began the following month, organized into repeating 243-day cycles, exactly the time it takes Venus to complete one full rotation beneath Magellan's orbit, letting the spacecraft methodically image the entire planet as it turned underneath, piece by piece. By the time its primary mapping was complete, Magellan had captured detailed radar images covering roughly 98 to 99% of the Venusian surface, more digital data, at the time, than every previous American planetary mission combined. Later, engineers tested something called aerobraking, deliberately dipping the spacecraft into the uppermost edge of Venus's atmosphere over and over, using pure atmospheric drag instead of fuel to reshape its orbit for even more precise gravity measurements. Finally, on October 12, 1994, in a planned and deliberate ending, controllers sent Magellan diving into the thick Venusian atmosphere itself. The signal went silent at 10:02 UTC, and the spacecraft was presumed destroyed the following day, having spent 4 years quietly mapping a world no camera could ever have shown us. Jupiter, meanwhile, would get a second visitor of its own, one that had to solve a problem Galileo never fully faced, staying alive in one of the most violently radio-captive environments in the entire solar system. NASA's Juno spacecraft launched on August 5, 2011, and after a 5-year, roughly 1.74 billion-mile journey that included its own Earth flyby gravity assist in 2013, arrived at Jupiter on July 4, 2016. Getting captured into orbit meant firing Juno's main engine for about 35 minutes, changing its speed by more than 1,200 miles per hour, in a maneuver that, exactly like Galileo's stuck antenna and exactly like New Horizons' 23-second burn at Pluto, had to be carried out entirely on the spacecraft's own authority. If that engine had fired even slightly wrong, in timing or direction or duration, Juno would simply have sailed past Jupiter and out into deep space, permanently, with absolutely no way for anyone on Earth to catch it or bring it back. For the full 35 minutes of that burn, Juno's own solar panels were turned away from the Sun, a genuinely risky position for a solar-powered spacecraft to sit in for nearly 2 hours total, while controllers back on Earth watched the whole thing unfold through signals gathered by the Deep Space Network's largest dishes, the 70-meter antennas at Goldstone and Canberra, working together with smaller 34-meter dishes at those same two sites. It worked, and it worked exactly as predicted, and NASA's own project officials afterward called the insertion tricky but flawless. To actually survive at Jupiter long-term, Juno flies a deliberately engineered polar orbit, the first any spacecraft has ever used around a gas giant, threading a narrow path that repeatedly ducks between the planet itself and the most lethal parts of its radiation belts, rather than flying straight through them. Even with that careful design, Jupiter's radiation is so severe that over the course of roughly a year, Juno absorbs a cumulative dose equivalent to about 60 million dental X-rays, and several of its instruments, including its own camera, were originally expected to survive only through the mission's 8th orbit. During the single riskiest moment of the entire mission, the orbit insertion burn itself, every one of those instruments, camera included, was deliberately switched off because there was no scientific data worth risking on a maneuver the whole mission's survival depended on. Juno went on to complete 35 orbits during its prime mission alone, gathering more than 3 terabits of science data, and its mission has since been extended multiple times, keeping it, as of the most recent figures gathered for this research, NASA's most distant active planetary orbiter. Which brings us to Voyager, probably the single best real-world proof that this whole system actually works exactly as intended, and also the best example of just how fragile that connection can be, even after nearly 5 decades of success. Voyager 1 and Voyager 2, both launched in 1977, sent out on what NASA called a grand tour of the outer solar system, visiting Jupiter, Saturn, Uranus, and Neptune. By 1989, they'd completed that planned tour and kept right on going, sailing outward past the edge of the planets entirely. In 2012, Voyager 1 became the first human-made object in history to leave the solar system and cross into interstellar space. Voyager 2 followed it out in 2018. To this day, they remain the only 2 spacecraft ever to operate beyond the heliosphere, the vast bubble of magnetic fields and charged particles that the Sun projects out into the galaxy, far past even the orbit of Pluto. As of a report published in August of 2023, Voyager 1 sat nearly 15 billion miles from Earth, roughly 24 billion kilometers of empty space between it and home. And keep in mind, both spacecraft were originally designed for a 12-year mission. NASA has kept them running for more than 4 times that long. Before we get to how close both of those spacecraft came to going silent forever, it's worth pausing on something they carry that has nothing to do with navigation at all, and everything to do with why people care so much about keeping them talking. Bolted to the side of each Voyager spacecraft is a gold-plated copper phonograph record, launched aboard Voyager 2 on August 20, 1977, and aboard Voyager 1 on September 5, 1977. It was assembled by a team led by the astronomer Carl Sagan, along with his collaborator Anne Druyan, and it contains 115 images, spoken greetings recorded in 55 different human languages, natural sounds recorded here on Earth, and 27 musical selections gathered from cultures around the world. The whole thing is sealed inside a protective aluminum cover, etched with a diagram marking the positions of 14 pulsars, meant to let any future finder calculate exactly when and from where the spacecraft was launched. A tiny sample of uranium-238 was even embedded in that cover, specifically so that its radioactive decay could be used, one day, to work out precisely how old the record actually is. Engineers designed the whole assembly to survive for roughly 1 billion years. It spins at a slower speed than a normal record, 16 2/3 revolutions per minute, which let the team pack nearly 90 minutes of audio onto it, and each copy carries a hand-etched inscription, a message, in essence, to the makers of music across all worlds and all time. NASA calculated the aluminum cover could withstand something like 4,000 tiny impacts from cometary dust before the spacecraft ever leaves the solar system's outer boundary. Sagan himself estimated it would be roughly 40,000 years before either Voyager comes anywhere close to another star system, and current projections suggest Voyager 1 will eventually pass within about 1.6 light-years of a star called Gliese 445. So every single command sent to keep Voyager 1 and Voyager 2 alive, every antenna repositioning, every troubleshooting session across billions of kilometers, isn't just about protecting a scientific instrument. It's about keeping a genuine physical message from an entire civilization from going dark before it's even had the chance to begin its real journey. The Voyagers weren't actually the first spacecraft to carry that kind of message either. The idea itself was already 5 years old by the time the Golden Record left Earth. NASA's twin Pioneer 10 and Pioneer 11 spacecraft, launched March 2, 1972 and April 5, 1973, were the very first human-made objects on trajectories fast enough to escape the solar system entirely, and bolted to each of their antenna support struts was a small gold-anodized aluminum plaque, just 6 inches by 9 inches, positioned specifically to shield it from erosion by interstellar dust over the eons ahead. The whole idea started almost casually when a science journalist named Eric Burgess suggested to Carl Sagan, the same Carl Sagan who would later lead the Golden Record project, that these particular spacecraft, since they were leaving the solar system for good, ought to carry some kind of message. NASA agreed and gave Sagan just 3 weeks to design one. Working with Cornell astronomer Frank Drake, famous for the Drake equation, Sagan built a plaque that tried to explain humanity to a mind that might share none of our biology, none of our language, and none of our culture. A diagram of the hydrogen atom in its 2 simplest states, meant to establish a universal unit of time and distance any advanced civilization would presumably recognize. A map of 14 pulsars, their positions used to pinpoint exactly when and where in the galaxy the spacecraft had come from. The very same basic idea Sagan's own team would reuse, 5 years later, on the cover of the Golden Record, a simple diagram of the solar system itself, and outlined figures of a human man and woman, drawn to scale, by Sagan's wife at the time, the artist Linda Salzman Sagan. Only 3 of these plaques were ever made, 1 for each spacecraft and a single spare kept by NASA, all of them engraved at a small shop in San Carlos, California. The plaques weren't universally well received back on Earth. Contemporary newspapers in 1972 ran letters from readers objecting to the nude human figures on a NASA spacecraft, a small but telling reminder that a message built for beings who might not exist yet still had to first get past the people who were sending it. Pioneer 10 went on to cross the orbit of Neptune in 1983, becoming, at that moment, the most distant human-made object from the Sun, a record Voyager 1 would eventually take over. 2 tiny gold plaques, riding quietly past the edge of everything we know, years before anyone thought to press a golden record into copper and send it out to follow them. That kind of longevity, and that kind of stakes, don't come without close calls, and 2023 delivered 2 of the most dramatic ones in the entire Voyager program. The first happened to Voyager 2 in July of that year. On July 21, 2023, flight controllers sent Voyager 2 a routine, planned series of commands, the kind of thing that had been done successfully thousands of times before. Except this time, something went wrong. The commands accidentally caused the spacecraft's antenna to tilt just 2 degrees away from its precise pointing at Earth. 2 degrees. That's all it took. Voyager 2 immediately lost the ability to receive any further commands, and it stopped transmitting data back to Earth entirely. At that exact moment, Voyager 2 was more than 12 billion miles away, and a radio signal traveling at the speed of light needed over 18 hours just to cover that distance in one direction. And here's the detail that makes the whole situation feel almost impossibly fragile. Only one single antenna on the entire planet was even capable of communicating with Voyager 2 at all, because of where it sits in the sky relative to the southern hemisphere. That antenna is Deep Space Station 43, a 70-meter dish at the Canberra Deep Space Communication Complex in Australia, operated by CERO. If that dish couldn't reach the spacecraft, nothing could. And this wasn't even the spacecraft's first extended silence. 3 years earlier, in 2020, Voyager 2 and the Deep Space Network had already gone through a full 7-month stretch without being able to communicate at all. So the team going into July 2023 already understood, intimately, just how long these gaps could stretch. For 11 days, there was silence. Then, on August 1st, 2023, NASA's team detected something, a faint but unmistakable heartbeat signal coming from Voyager 2, picked up by the Deep Space Network. It wasn't full communication, but it confirmed the 46-year-old spacecraft was still alive, still functioning, still out there. The following day, engineers at the Canberra complex attempted something NASA itself described as a long shot. Using the most powerful transmitter available at that site, they essentially shouted a single command out into the void, aimed at where they calculated Voyager 2's misaligned antenna should still be able to catch it, hoping to nudge it back those 2 crucial degrees toward Earth. The signal took over 18 hours to arrive. Then the team had to wait almost another full day just to find out whether it had worked at all. And on August 4th, 2023, the wait ended when Voyager 2 began transmitting data again. The fix had worked. If it hadn't, NASA's backup plan was simply to wait until October, when the spacecraft was scheduled to perform an automatic internal reset that would have corrected its orientation on its own, months later, with no guarantee of exactly when or how. As if that wasn't enough drama for 1 year, Voyager 1, the older and more distant of the 2 twins, developed its own serious problem just a few months later. Starting in mid-November of 2023, Voyager 1's transmissions to Earth stopped making sense. The spacecraft communicates using binary code, strings of ones and zeros that get translated into meaningful data on the ground, and suddenly, those ones and zeros simply stopped adding up to anything coherent. Engineers eventually traced the likely source of the problem to something called the Flight Data System, or FDS, and specifically to a suspected issue in its memory, the component responsible for storing the spacecraft's performance instructions. Solving this problem meant working at a truly staggering distance. Voyager 1's total round-trip communication path, out to the spacecraft and back, adds up to roughly 30 billion miles, meaning every single diagnostic command NASA sent required nearly 2 full days before any kind of response could even theoretically arrive. Engineers spent months working through this puzzle, one incredibly slow exchange at a time. Finally, on April 20th, 2024, NASA confirmed that an initial fix had worked, and 2 days later, on April 22nd, the agency officially announced it once again had clear, usable information about Voyager 1's health and status. Additional commands, designed to rebuild the rest of the FDS system's lost code and eventually restore full science data, were scheduled to follow in the weeks after that. Through all of it, Voyager 1's twin, Voyager 2, kept operating normally the entire time, never missing a beat while its sibling spacecraft sat mute for months, 24 billion kilometers from anyone who could reach out and fix it directly. If Galileo is a story about recovering from disaster over years, and Voyager is a story about the constant maintenance required to keep something alive for decades, New Horizons is the opposite of both, a story about a single mission with exactly one opportunity to get everything right, on one unrepeatable pass through space, where the margin for error was measured not in years, but in seconds and miles. New Horizons launched on January 19, 2006, as part of NASA's New Frontiers program, with one primary goal: become the first spacecraft in history to explore Pluto up close. It picked up a gravity assist from Jupiter on February 28, 2007, using the giant planet's momentum to sling itself further out into the solar system, and then it spent years quietly crossing the enormous gap between Jupiter and Pluto. As the spacecraft entered its final approach in the spring and summer of 2015, timing became everything. Because unlike a car correcting course on a highway, New Horizons had exactly one opportunity to get this right. There would be no second flyby, no do-over. In the final days before arrival, the navigation team combined radio tracking data from the Deep Space Network with optical images captured by the spacecraft's own LORRI camera, comparing Pluto's exact position against the background stars to sharpen their estimate of precisely where the dwarf planet actually was. This work involved not one team, but three, cross-checking each other's math across three different organizations: the mission team at Johns Hopkins Applied Physics Laboratory, the primary navigation team at a company called Kinetex Aerospace, and an entirely independent second opinion navigation team at NASA's own Jet Propulsion Laboratory, all working in parallel before the spacecraft committed to its final approach. Given what happened to Mars Climate Orbiter just a few years earlier, that kind of redundant, cross-checked math wasn't a formality. It was exactly the kind of safeguard the earlier failure had made painfully necessary. Based on that combined data, the team commanded a short thruster firing that began at 11:01 p.m. Eastern Time on June 29, 2015, and lasted just 23 seconds. 23 seconds of engine burn, calculated to the second, to correct a trajectory across nearly 3 billion miles of space. Confirmation that the maneuver had gone exactly as planned reached mission control at Johns Hopkins Applied Physics Laboratory via the Deep Space Network at 5:30 the following morning. At the moment that correction was made, New Horizons was still about 10 million miles from the Pluto system itself, and nearly 3 billion miles from Earth. Here's what makes that 23-second burn so remarkable. According to Yanping Guo, the mission's design lead at Johns Hopkins APL, if that final adjustment hadn't happened, New Horizons would have arrived at its target 20 seconds late, and would have missed its intended position by 114 miles. That might not sound catastrophic until you understand what those measurements depended on. As New Horizons flew past Pluto, radio signals sent from Earth were timed to arrive at the exact moments the spacecraft passed through the shadows cast by Pluto and its largest moon, Charon, allowing scientists to study Pluto's thin atmosphere as sunlight and radio waves passed through it. Every one of those measurements depended on commands stored in the spacecraft's onboard computer, programmed in advance to fire at precise, predetermined instants. 20 seconds and 114 miles doesn't sound like much across billions of miles of travel, but at the moment of closest approach, that margin was the difference between capturing the science NASA had spent 9 years and a 9-year journey to obtain, or missing it entirely. The flyby itself happened at 11:49 and 57 seconds Coordinated Universal Time on July 14, 2015, with New Horizons passing about 12,500 kilometers, roughly 7,800 miles, above Pluto's surface. 13 minutes later, it swept past Charon at a distance of about 29,431 kilometers. And then, because the spacecraft was entirely focused on gathering data rather than transmitting it during the flyby itself, everyone back on Earth had to simply wait. About 13 hours after closest approach, at 12:53 a.m. UTC on July 15th, a 15-minute burst of status messages finally reached mission operations through the Deep Space Network, confirming what engineers had spent nearly a decade preparing for. The flyby had worked, completely and successfully. New Horizons didn't stop there. It went on to fly past a distant, icy Kuiper Belt object called Arrokoth on New Year's Day, 2019, at a distance of just 3,500 kilometers, making it, at the time, the most distant object humanity had ever explored up close. As of the most recent figures compiled for this research, the spacecraft has passed roughly 60 times Earth's own distance from the Sun, putting it about twice as far out as Pluto itself was during that historic 2015 flyby, and it's still traveling outward at around 14 kilometers every single second. Where New Horizons proves that precision can come down to a single 23-second engine burn, Cassini proves the opposite lesson, that some missions succeed not through one perfect moment, but through hundreds of small, careful corrections, made patiently, over more than a decade, and along the way, Cassini also carried a passenger whose own story is arguably the single closest call in this entire history. Cassini-Huygens launched on October 15, 1997, and spent the next 7 years simply getting to Saturn, using gravity assists from Venus, Earth, and Jupiter along the way to build up enough speed for the journey. Attached to its side for that entire 7-year cruise was a small European-built lander called Huygens, designed to detach from Cassini upon arrival and parachute down through the thick, hazy atmosphere of Saturn's largest moon, Titan, a world so shrouded in orange smog that almost nothing was known about what actually lay beneath it. In the year 2000, still years before arrival, a group of ESA engineers, including one named Boris Smeds, the head of a systems and requirements section at ESA's operations center in Germany, started asking an uncomfortable question. Had the radio link between Huygens and Cassini's onboard receiver actually been tested thoroughly enough to guarantee it would work? Smeds pushed for an extensive round of testing that some mission managers initially considered unnecessary, using NASA's own Deep Space Network ground stations and an exact duplicate of the Huygens hardware to simulate, as closely as possible, the actual conditions the real descent would create. In February of 2000, those tests confirmed something genuinely alarming. As Huygens plunged into Titan's atmosphere and rapidly decelerated, the resulting Doppler shift in its radio signal wouldn't just change its frequency, it would also compress the timing of its data pulses just enough that Cassini's receiver, as originally built, would fail to properly recognize the incoming data at all. In practice, this meant that without a fix, the vast majority of Huygens' hard-won science, gathered during a landing that could never be repeated, would have come through as unusable noise. And because both spacecraft were already deep in interplanetary space by the time this was discovered, there was no way to simply swap out a faulty part. The only tool available was trajectory itself. Engineers spent the following years reworking Cassini's entire path to Titan, redesigning the orbiter's planned flyby distance from a close pass of around 1,200 kilometers out to a far more distant 60,000 kilometers, specifically to slow the relative velocity between the two spacecraft enough to bring that dangerous Doppler shift down into a range the receiver could actually handle. It took hundreds of engineers working across NASA and ESA to re-engineer a mission that was already flying. Huygens finally separated from Cassini on December 25, 2004, and coasted alone for roughly 3 weeks before striking Titan's atmosphere on January 14, 2005, deploying its main parachute within about 4 minutes and beginning a descent that would last well over 2 hours. At 11:38 that same day, Universal Time, Huygens touched down on Titan's surface at a gentle 4.54 meters per second, becoming the first, and to this day, the only, spacecraft ever to land successfully anywhere in the outer solar system at a distance so great that its signal, relayed through Cassini, still took about 67 minutes to cross the more than 1.2 billion kilometers back to Earth. And here's the part that makes this story almost unbearably human. Even after the entire mission had been redesigned around Smeds' discovery, even after Cassini's flyby distance had been completely reworked to solve the Doppler problem, Huygens' signal was still designed to travel back through 2 separate, redundant channels, Channel A and Channel B, so that if anything at all went wrong with one, the other would still carry a complete copy of the data. Somewhere in the final sequence of commands, the instruction to actually switch on Cassini's reception of Channel A was simply never loaded. Nobody was listening on that channel at all. Channel B worked flawlessly, without a single dropout, and most of Huygens' science survived because of it. But roughly half of the probe's planned surface images, out of about 700 originally intended, never arrived, and its wind experiment, which depended entirely on that missing channel, lost its primary data outright, salvaged only partially, afterward, by radio telescopes back on Earth that happened to also be listening to Huygens directly. A mission that survived a genuinely difficult, deeply technical failure, discovered years in advance, still lost half its haul to a single command that nobody double-checked. Huygens kept transmitting from Titan's frozen, ice-pebble-strewn surface for about 72 minutes after landing, until Cassini's own orbit finally carried it out of view, and the connection, for good, went quiet. Cassini itself, meanwhile, went on to spend 13 years in orbit around Saturn, more than 3 times its original 4-year planned mission, because virtually everywhere it looked, it found something nobody expected: a global ocean hiding beneath the icy surface of the small moon Enceladus, with signs of hydrothermal activity, methane lakes and complex organic chemistry on Titan itself, a ring system that turned out to be far more dynamic and active than anyone had predicted. None of that longevity would have been possible without an enormous amount of quiet, ongoing navigation work, because Cassini simply didn't carry enough fuel to do it the brute force way. The spacecraft launched with less than 1/30th of the propellant it would eventually need for every trajectory change over its lifetime. Instead, Cassini's navigation team used repeated flybys of Titan, almost like stepping stones, using the moon's own gravity, over and over, to reshape Cassini's path through the Saturn system without spending fuel it didn't have. Over the full life of the mission, Cassini completed 294 separate orbits of Saturn and made hundreds of trajectory corrections along the way, essentially using the stars and precise tracking from the Deep Space Network, the same way ancient sailors once used the night sky to find their way across open ocean. By 2017, after 13 years, Cassini was finally running low on fuel, and NASA had a decision to make. Rather than simply let the spacecraft drift, uncontrolled, with even a small risk that it might eventually crash into and contaminate one of Saturn's potentially life-hosting moons with hitchhiking Earth microbes, mission planners designed an ending, the grand finale. Starting in April of 2017, a final close flyby of Titan on April 22nd used the moon's gravity one last time to bend Cassini's trajectory into an entirely new kind of orbit, one that would carry the spacecraft repeatedly through the roughly 1,200-mile-wide gap between Saturn itself and the innermost edge of its rings, a region no spacecraft had ever dared enter before. Over the following 5 months, Cassini completed 22 of these proximal orbits, its altitude above Saturn's cloud tops shifting between roughly 1,000 and 2,500 miles, depending on the specific pass. During 6 of those 22 orbits, while the spacecraft's antenna maintained contact with Earth, scientists used the tiny Doppler shift in Cassini's radio signal, sent out from Earth at one frequency and returned by the spacecraft's onboard transponder at another, to directly measure Saturn's gravity field for the first time in this kind of detail, turning a navigation and communication system into a genuine scientific instrument probing the interior of a planet nearly 1 billion miles away. And then, on September 15, 2017, Cassini's mission ended exactly as engineers had designed it to. On its final orbit, the spacecraft's trajectory was deliberately aimed to intersect Saturn's atmosphere, and its small thrusters worked to keep its antenna locked onto Earth for as long as physically possible, transmitting real data about the composition of Saturn's upper atmosphere in something close to real time. Right up until the very end, Cassini kept transmitting for about 30 seconds longer than engineers had even expected, before finally breaking apart and burning up completely in the atmosphere of the planet it had spent 13 years quietly studying. Saturn wasn't the only small body in the solar system where a European mission tried to land against near-impossible odds, either. And the story of that landing shows just how much can still go wrong, even when the physics behind it and the tracking systems watching over it work exactly as intended. In November of 2014, the European Space Agency's Rosetta mission arrived at comet 67P/Churyumov-Gerasimenko, after a journey of roughly 6.4 billion kilometers and more than 10 years, using multiple gravity-assist flybys of Earth and Mars to build up enough speed and reach the comet's orbit. Rosetta carried a small lander called Philae, and after weeks of studying the comet's surface, mission scientists selected a smooth, relatively safe-looking patch on the smaller of the comet's 2 lobes, a site they named Agilkia. The night before the scheduled landing, engineers discovered a serious problem. Philae's small active descent thruster, designed to push the lander gently downward and counteract the recoil of its landing harpoons firing, could not be activated. The team proceeded anyway, deciding to rely entirely on the harpoons and a set of ice screws built into Philae's 3 feet. Philae separated from Rosetta on November 12, 2014, at about 8:35 in the morning GMT, beginning a 7-hour, entirely autonomous free-fall descent toward the comet's surface, descending at a gentle walking pace of roughly 2 miles per hour. Because the round-trip radio delay between Rosetta and Earth at that distance came to roughly 28 minutes each way, there was no possibility whatsoever of any real-time human control during the descent. Every single stage of the landing had to be pre-programmed and carried out entirely on its own. Confirmation of that first touchdown finally reached Earth at 16:03 GMT, relayed through Rosetta and received simultaneously by ESA's ground station in Argentina and NASA's Deep Space Network station in Madrid. But the landing hadn't gone as planned. Philae's anchoring harpoons had failed to fire, and combined with the comet's almost non-existent gravity, roughly 100,000 times weaker than Earth's, the lander bounced. It rose nearly a kilometer above the surface, drifted a similar distance sideways, and came back down, bounced a second time, and finally settled after a total of 4 separate contacts with the ground, almost 2 hours after that very first touchdown. Because an automatic science sequence had already triggered on that first contact, Philae's instruments kept working throughout the unplanned 2-hour bounce across the comet's surface, accidentally gathering measurements from more than one location instead of just one. It finally came to rest in a spot later named Abydos, roughly a kilometer from its intended landing site, wedged partly in shadow, which severely limited how much sunlight its solar panels could gather. Its main battery lasted only about 60 hours before Philae fell silent. It briefly reawakened months later, in 2015, as the comet's position relative to the Sun shifted and its panels caught a little more light. But full, reliable contact was never restored, and by early 2016, mission engineers stopped sending commands altogether, concluding that hearing from Philae again had become vanishingly unlikely. Not every close encounter in deep space involves landing at all either, and one of the more remarkable examples never actually touched down on anything larger than a rock. NASA's OSIRIS-REx spacecraft launched on September 8, 2016, and reached the near-Earth asteroid Bennu in December of 2018. Bennu is small, only about 500 meters across, a third of a mile, but when OSIRIS-REx arrived, it found the asteroid's surface far rockier and more hazardous than mission planners had expected, covered edge to edge in boulders, without a single site that met the original safety standards the team had planned around. The spacecraft's navigation, handled by the same Kinetex aerospace team that had helped guide New Horizons safely past Pluto years earlier, working alongside NASA's Goddard Space Flight Center, eventually settled Bennu into a series of increasingly close orbits, at one point coming within about a kilometer of the asteroid's center, the closest orbit any spacecraft had ever achieved around a small body in the solar system. Eventually, the team selected a landing zone barely 16 meters wide, tucked inside a crater named Nightingale, and hemmed in on every side by boulders larger than the spacecraft itself. On October 20, 2020, OSIRIS-REx attempted something it had never done before and would only get a handful of chances to repeat: a touch-and-go sample collection, nicknamed TAG. The spacecraft descended from a safe holding orbit about 770 meters above Bennu's surface, extended its robotic sampling arm, folded its solar panels up and back into a shape engineers nicknamed the Y-wing configuration, both to protect them and to shift the spacecraft's balance directly over its sampling head, and then slowly, carefully, drop toward the surface. Because a radio signal takes nearly 20 minutes to cross the roughly 200 million miles separating Bennu from Earth, there was, once again, no possibility of real-time human control. The entire descent was guided by an onboard optical system called natural feature tracking, which compared live camera images against detailed digital maps of Bennu's own surface, allowing the spacecraft to calculate its exact position and speed entirely on its own, all the way down. Contact with the surface happened at 21:53 UTC, and confirmation reached NASA's team on Earth at 6:08 that evening, Eastern Time. The spacecraft's sampling head touched Bennu's surface for somewhere between 5 and 6 seconds, most of the actual sample collection happening within the first 3 seconds alone, before OSIRIS-REx fired its thrusters and pulled itself back away from the asteroid to a safe distance. When engineers checked the results, the touchdown had landed within about 3 feet, roughly 1 meter, of its intended target, on a world so small that even a modest boulder could have ended the mission instantly. And the sampling mechanism itself turned out to work almost too well. A burst of nitrogen gas, designed to stir loose material into a small collection chamber, kicked up so much rock and dust that it jammed open the flap meant to seal the sample safely inside. OSIRIS-REx left Bennu the following year and delivered its sample capsule back to Earth in September of 2023, closing out a mission where the single riskiest moment, touching down on an alien world only a third of a mile wide, from 200 million miles away, had to be trusted entirely to the spacecraft itself. Not every navigation story in this field involves years of careful planning or a single dramatic engineering flaw, though. Some of the most dangerous moments in deep space exploration happen in a matter of minutes, on a world so far away that Earth can't help at all, even if something starts to go wrong in real time. Landing anything safely on the surface of Mars means solving a problem that has nothing to do with the careful, patient navigation used for something like Cassini, and everything to do with speed and total autonomy. The entire process, called entry, descent, and landing, or EDL for short, has to happen completely on its own, with no human input whatsoever, simply because there isn't time for Earth to help. When NASA's Perseverance rover approached Mars on February 18, 2021, the spacecraft struck the top of the Martian atmosphere, traveling at somewhere around 12,000 to 12,500 miles per hour. From that instant, the entire sequence, atmospheric entry, a supersonic parachute deployment, a heat shield separation, a radar-guided descent, and finally, a bizarre and daring sky crane maneuver that lowered the rover itself down to the surface on cables, had to unfold in roughly 7 minutes. On landing day, Mars sat about 126 million miles from Earth, and even at the speed of light, a radio signal needed roughly 11 minutes to cross that distance in one direction. Do the math on that, and you land on something genuinely unsettling. The entire high-speed, high-risk landing sequence was over, one way or another, before Mission Control on Earth had even received the signal, confirming the spacecraft had reached the top of the atmosphere and started descending. As one NASA engineer put it at the time, there was no joysticking involved, none at all. By the time any problem could have been seen and diagnosed from Earth, the outcome, good or bad, would already be a matter of history. Engineers gave this entire sequence a name that's become famous for a reason: the 7 minutes of terror. It's not a new problem either. NASA's Curiosity rover faced the exact same challenge back in 2012, needing to go from roughly 13,000 miles per hour to a complete stop in about 7 minutes, using that same kind of hovering sky crane system to gently lower the rover onto the Martian surface on cables. For Perseverance, the team added a new refinement called range trigger, a system that determined the precise, optimal moment to deploy its enormous 70.5-foot wide supersonic parachute based on the spacecraft's real-time calculated position relative to its intended landing site, deploying at an altitude of about 7 miles. About 20 seconds after that parachute opened, the protective heat shield separated, finally exposing a landing radar that began bouncing signals directly off the Martian ground to calculate the spacecraft's exact altitude as it fell. According to NASA's own deputy project manager for the mission, Matt Wallace, the flight software controlling all of this ran to roughly 2 million lines of code, with something like 30,000 individual parameters that all had to be correctly configured in advance, because once the spacecraft hit the atmosphere, there would be no opportunity to fix a single mistake. Historically, by the way, roughly half of every mission ever sent to land something on the surface of Mars has failed. Perseverance's success, at 3:55 in the afternoon Eastern Time on February 18, 2021, wasn't a guarantee. It was the product of a machine trusted to fly itself, faster than any signal could reach it, through the single most dangerous 7 minutes of its entire mission. Not every navigation challenge in deep space is about danger, though. Sometimes it's about permanence, about accepting, from the very beginning, that a spacecraft is going somewhere it can never be physically reached again. The James Webb Space Telescope launched on Christmas Day, December 25, 2021, aboard a European Ariane 5 rocket. Its destination wasn't a planet or a moon at all, but an invisible point in space called the second Sun-Earth Lagrange point, or L2, a spot roughly 1 million miles from Earth, where the combined gravity of the Sun and Earth create a kind of natural parking spot, stable enough for a spacecraft to settle into without constantly burning huge amounts of fuel to stay in place. Getting there still required extraordinary precision. In the first 7 hours after launch, the Deep Space Network worked together with a European tracking station in Malindi to determine Webb's exact orbit, data that was used to plan the observatory's very first course correction, carried out about 12.5 hours after liftoff. On January 24, 2022, Webb fired its thrusters for nearly 5 minutes, 297 seconds, to complete its final post-launch correction and settle into orbit around L2. That final burn added only about 3.5 miles per hour to the spacecraft's speed, barely more than a brisk walking pace, just enough of a nudge to ease it precisely into its intended 6-month halo orbit. Here's the detail that makes Webb genuinely different from almost everything else in this story. It's parked 1 million miles away, permanently, by design, specifically because that isolation and that stability is what lets its instruments get cold enough to detect the faint infrared light of galaxies from the dawn of the universe. But that same distance means Webb can never be visited, repaired, or refueled the way earlier space telescopes sometimes were. For the rest of its working life, the telescope loops around L2 at distances that vary between roughly 117,000 miles from that exact gravitational point. And because the sun's radiation constantly pushes, ever so gently, against Webb's enormous sun shield, the observatory has to periodically fire its thrusters just to hold its position, a maneuver engineers call station keeping, originally planned to happen roughly once every 3 weeks, alongside separate maneuvers to manage the slow buildup of spin in its internal reaction wheels. Every one of those tiny burns draws down a fixed, finite supply of propellant that can never be replenished, which means Webb's entire working lifetime is, in a very real sense, being counted down by a fuel gauge that started ticking the moment it settled into orbit, watched over, the whole time, by precise tracking from the same deep space network that guides everything else in this story. And then there's a mission that flips this entire idea of navigation completely on its head, one where the goal isn't reaching a stable, distant point at all, but deliberately, repeatedly, falling as close as physically possible to the most dangerous object in the entire solar system. NASA's Parker Solar Probe launched in 2018, built and operated by the Johns Hopkins University Applied Physics Laboratory, and it holds a distinction no other NASA mission can claim. It's the first one ever named for a scientist who was still alive to see it launch. Physicist Eugene Parker had first predicted the existence of the solar wind back in 1958, and he was there, at 91 years old, watching as the spacecraft bearing his name lifted off toward the star he'd spent his career studying. Getting close to the sun turns out to be one of the hardest navigation problems in all of spaceflight. Not because it's technically hard to fall toward something with that much gravity, but because doing it safely and slowly enough to actually study anything requires bleeding off an enormous amount of orbital energy first. Parker Solar Probe's solution was to use the planet Venus over and over as a kind of natural break, 7 separate gravity assist flybys, each one trimming the spacecraft's orbit a little tighter, pulling it a little closer to the sun with every pass. Its 7th and final Venus flyby happened on November 6, 2024, swinging past the planet at a distance of just 376 kilometers, setting up the spacecraft's final, closest orbital configuration. The numbers that came out of that final setup are almost hard to process. Back in October of 2018, Parker Solar Probe had already broken the all-time speed record for a human-made object, surpassing roughly 153,000 miles per hour relative to the Sun, and beating a record that had stood since 1976. But on December 24, 2024, Christmas Eve, the spacecraft made its closest approach yet, passing just 3.8 million miles above the Sun's actual surface, a distance so small on a solar scale that it counts as effectively touching the outer edge of the Sun's atmosphere. At that exact moment, Parker Solar Probe was traveling at about 430,000 miles per hour, close to 692,000 kilometers per hour, or roughly 192 kilometers covered every single second, a speed formally recognized by Guinness World Records as the fastest any human-made object has ever traveled. At that kind of velocity and that kind of proximity to the Sun, real-time control from Earth isn't just difficult, it's flatly impossible. the spacecraft has to execute its closest approach entirely on its own, protected by an 11-centimeter thick carbon composite heat shield that reaches temperatures around 1,370 degrees Celsius on its sun-facing side, while the instruments tucked safely in its shadow stay close to room temperature the entire time. After a pass like that, there's nothing for the team back at Johns Hopkins to do but wait, exactly the way engineers waited after Voyager 2's antenna slipped, exactly the way controllers waited during Perseverance's 7 minutes of terror for a single scheduled signal, a beacon tone, confirming the spacecraft made it through. Following that record-setting December 2024 pass, that confirmation reached the Mission Operations Center on December 26th. 2 days of silence for a spacecraft that had just set the fastest speed record in human history, simply because there was no other way to know. So that's where we stand today, a network of enormous dishes spinning with the Earth, bouncing radio waves off spacecraft billions of miles away, and turning the delay of that signal into precise knowledge of exactly where something is and where it's going. But NASA isn't satisfied with radio alone, because radio has one unavoidable limitation. It requires Earth. Every technique described so far depends on a signal traveling all the way back to one of 3 dishes on our planet, being processed, and a response being sent all the way back out. For a mission traveling deep into interstellar space, decades from now, that round trip could stretch into days, even years. So engineers have started looking for ways for a spacecraft to figure out where it is entirely on its own, without needing to phone home, and that idea is a lot older than most people realize. Back on October 24, 1998, NASA launched a spacecraft called Deep Space One, built for one specific purpose: testing risky new technologies in actual spaceflight, before anyone trusted them on a real science mission. Among the 12 experimental systems packed onto that spacecraft was something engineers nicknamed AutoNav, the first ever onboard system built to let a spacecraft calculate its own position in the solar system, entirely by itself, using nothing but its own camera. The idea leaned on a principle anyone can test sitting in a chair. Hold a finger up in front of your face, close one eye, then the other, and watch how much your finger seems to jump against the background behind it. That's parallax, and it works the same way in space. Because asteroids in the inner solar system sit relatively close to a passing spacecraft, they visibly shift position against the much more distant, effectively fixed backdrop of stars. So roughly once a week, mission controllers would upload a pre-selected list of bright asteroids to use as reference points, and Deep Space One would spend a several-hour block of time turning its own camera toward each one in sequence, photographing them against the stars, and using that data to calculate, on its own, exactly where it was and where its own ion engine needed to point for the week ahead. On November 17, 1998, under the guidance of mission engineer Mark Raman, AutoNav ran its first major in-flight test successfully, doing precisely that. The same spacecraft also carried the first ion engine ever used as a primary means of propulsion, trading the brute force of chemical rockets for a slow, steady trickle of thrust from electrically charged xenon gas, a technology validated well enough on Deep Space One that it later powered NASA's Dawn mission to the asteroid Vesta and the dwarf planet Ceres. The autonomous navigation software itself lived on too, refined and reused to help guide the Stardust mission precisely to the nucleus of a comet, and to help NASA's Deep Impact mission strike another comet's unpredictable path with an impactor of its own. Deep Space One proved something simple but important. A spacecraft didn't necessarily need Earth's permission or Earth's math to know where it was, and the answer engineers eventually landed on for pushing that idea even further, out past the reach of asteroids entirely, is almost poetic. Instead of using signals built by humans, or landmarks as close as the asteroid belt, use light created by dead stars. Pulsars are what's left behind after a massive star explodes as a supernova. What remains is an unimaginably dense, crushed core, something that can pack more mass than our entire sun into a sphere no larger than a city. And because of how they formed, pulsars spin incredibly fast, sweeping powerful beams of radiation around like a lighthouse, some of them completing a full rotation in a matter of milliseconds. From certain angles, that beam sweeps directly past Earth and passed everywhere else in the solar system, appearing as an extraordinarily regular, predictable flash, so regular that these flashes rival atomic clocks for precision. NASA tested exactly this idea using an instrument called NISA, the Neutron Star Interior Composition Explorer, launched to the International Space Station in June of 2017. Riding along inside NISA was a technology demonstration called Sextant, short for Station Explorer, for X-ray timing and navigation technology, built specifically to test something called X-ray pulsar navigation, or XNav, for the first time ever in actual spaceflight. The concept works by capturing individual X-ray photons streaming from a known pulsar, tagging the precise moment each one arrives, and comparing that arrival time against a detailed model of exactly when that pulsar's beam should have swept past. From the tiny differences between predicted and actual arrival times, onboard software can calculate range and velocity using nothing but starlight, the same underlying principle GPS uses with its precisely synchronized satellite signals, except stretched out to work anywhere in the galaxy. In January of 2018, NASA announced that this test had succeeded, the first demonstration in history of autonomous X-ray navigation performed in space. Jason Mitchell of NASA's Goddard Space Flight Center pointed out that while NISA itself is roughly the size of a washing machine, a dedicated navigation version of the same technology could eventually be built dramatically smaller. His colleague at Goddard, Luke Winternitz, framed the whole concept simply. GPS works because its signals are precisely synchronized, and pulsars offer that same kind of precision on a scale that spans the entire galaxy, not just the space around one planet. The idea isn't purely theoretical anymore either. A 2013 study led by George Hobbs of the Parkes Pulsar Timing Array project in Australia found that a spacecraft would need to observe at least 4 different millisecond pulsars, roughly once a week, to pin down its position using this method. And while the detectors required would be fairly large by spacecraft standards, the researchers found the whole approach was genuinely workable. China moved on the idea in 2016, launching a dedicated satellite called XPNav-1, carrying sensors built to detect X-rays from 26 nearby pulsars, and begin assembling what researchers call a pulsar navigation database, essentially a map of these cosmic lighthouses that future missions could reference. If this technology matures the way its developers hope, it could eventually give spacecraft heading toward the outer planets, or even beyond the solar system entirely, a way to know exactly where they are, without waiting days or years for a signal to crawl back home and a correction to crawl all the way back out. Which brings this full circle, back to that opening idea. Every single spacecraft humanity has ever sent past the moon has depended entirely on this fragile, remarkable chain, precisely timed radio waves, 3 enormous dishes spaced perfectly around a spinning planet, decades of engineering built by people who were once told by Nobel laureates that the whole idea was essentially impossible, and, again and again throughout this story, a margin for error measured in degrees, seconds, or minutes, standing between success and complete, permanent silence. Mariner 4 proved, in 1965, that the entire concept could work at all, turning a 20-second engine burn made months in advance into humanity's first close look at another world. Apollo 13 proved that when every computer on board goes dark, the oldest navigation tools in existence, a window, a landmark, and a steady hand, can still bring 3 astronauts home. And Artemis 1 proved, decades later, that the same kind of deep space stress test could be rehearsed safely, without a crew, before anyone's life depended on it again. Viking 1 proved that a machine could be trusted to land itself on an entirely alien world, using nothing but instructions written months earlier. Mars Climate Orbiter proved that a mission can survive 9.5 months of flawless deep space tracking and still be destroyed by 2 engineering teams using different units. Galileo proved that even a fully broken antenna doesn't have to mean a fully broken mission if the people on the ground are willing to reinvent the entire communication system from hundreds of millions of miles away. Magellan proved that radar could show us an entire planet's surface, even through clouds no camera could ever see past. Juno proved that a spacecraft could thread a needle through one of the most lethal radiation environments in the solar system on a single uninterruptible burn and come out the other side unharmed. Voyager 2 proved that a single misaligned antenna can nearly sever a 46-year-old connection to a spacecraft billions of miles from anyone who can reach out and physically fix it. Voyager 1 proved that even after 50 years of practically flawless operation, a garbled signal can leave engineers waiting nearly 2 full days just to hear a single, meaningful word back. The Pioneer and Voyager plaques and records proved that some of this was never only about data at all. New Horizons proved that on a single, unrepeatable pass through space, the difference between historic success and quiet failure can come down to a 23-second engine burn and a margin of just over 100 miles. Huygens proved that even a flaw caught years in advance and painstakingly engineered around can still lose half its data to nothing more than a command that never got loaded. Cassini proved that patient, decade-long navigation, borrowing gravity from a single moon over and over, can accomplish what raw fuel never could. Philae proved that even a perfect, textbook descent can still end in an unplanned 2-hour bounce across an alien world. OSIRIS-REx proved that a spacecraft can reach out and touch an asteroid a third of a mile wide, from 200 million miles away, and land within 3 feet of its target without a single human hand on the controls. Perseverance proved that sometimes the safest thing a spacecraft can do is fly itself, faster than any signal from Earth could ever arrive in time to help. Webb proved that some missions succeed by accepting, from day one, that they can never be reached again. And Parker Solar Probe proved that the same basic techniques used to explore the cold, dark edge of the solar system can also, carefully, be used to survive a deliberate dive toward the most violent object in it. That's deep space navigation. Not lasers, not tractor beams, not some sleek fictional autopilot. Just light, math, patience, measured in hours and days rather than seconds, and a network of dishes built by people who refused to accept that talking to the edge of the solar system was impossible. And somewhere out there right now, more than 20 billion kilometers from where you're sitting, 2 aging spacecraft are still listening for the next message, carrying a golden record that was never meant to be read anytime soon, still waiting on a signal that, if it ever truly stopped coming, would mean exactly what the title of this video promised. They'd be lost forever.